Yeah, so no, there is no recording for this yet, but there's about to be. So let's see how this goes. Can you see right away what's different between today's work and yesterday's work? Not just fractions. That's the key. There's numbers in front of the x squared, and they might be fractions. There might not be fractions. That turns out to be not really the issue. It's part of the issue. The fractions, unfortunately, are going to annoy some of us more than others. Those of you who have kind of ghetto basic skills, then you'll find this to be a bit more miserable, perhaps. And that's well, it's the way it is, right? So let's begin. And I know this is a homework assignment, but I think if we just dip around and pick a few and do them together, that this will help. So let's start with number one. And again, we're just kind of working through problems together here. So I will say this about the process. It doesn't change initially. So what we learned yesterday and the day before, or Thursday and yesterday, that part of it still stays the same. So we're going to go about our business as we would have before, meaning we're going to go find the vertex. And so what's my A value in number one? Right. So if A is 2, let me get my skinny pen here. So we agree that A is 2. And then we agree that B is negative 20. So we're still, this never will change, guys. If your quadratic's written in this form, and call it standard form, then this will always work. So the opposite of B divided by 2A is going to look like positive 20 divided by 2 times 2, which is 4. Opposite B divided by 2A. We learned this on Thursday. And then that's 5. So we can now say that the vertex is at a point named 5 something. And how, again, do we figure out the something? How do we complete that? Plug it back in. And right away, there becomes an order of operations issue. I love it if everyone hears this on the first go round. If your very first thought is the number 100, then you really need to listen carefully. I'm talking directly to you. Remember that when you put 5 in place of x, you don't do 2 times 5. You know that, right? You do 5 squared first. To do 2 times 5 and get 10 and then square it would be really egregious. And so remember that when you put the 5 in, you're just putting it into this little red jelly bean right here. And again, only that. So what is 5 squared? Well, what's 2 times 25? Good. So be very careful. Hold yourself accountable for those little 6th grade basics. Order of operations will always be a thing. It doesn't go away. And then we're going to go minus 20 times x. What's minus 20 times 5? Yeah, minus 100. And then plus 48. What's 50 minus 100? Negative 50 then plus 48. Good. So just like that, we have our vertex. And so that part of the process doesn't change. And that, I mean, that will always consistently work. Now, what changes is when we get to the vertex, there's a little bit of a shift. And that, by the way, that process of finding the vertex is going to get a little worse as you see fractions popping in. So sorry in advance, but this one's pretty peaceful. So we're going to first go to the vertex. We're going to go to the point 5, negative 2, and we're going to put a point there. So we're going to go right 5. It's not labeled, but of course you know where it's at, and down 2, and we're going to put a point. Now, ordinarily, and this is where I think today shines as something new. There's kind of 2 new things today. Number 1 is the brutality coming up of having to find the vertex with fractions. And number 2 is the structural changes that our parabolas undergo. So does anyone want to take a stab at what the graph is going to look like? First off, let me ask you this. Is it going to open up or down? It is. And we know that because that's already like something that we know. If it's a positive in front of the x squared, it's going to be a bowl and not an arch. What do you think the 2 does? Yeah, you're right. I did. And I didn't really go into detail because I knew that I would be talking about it today, but the 2 does something. It physically, structurally changes the graph. It definitely will, yes, it will physically alter the graph. It will either make it skinnier or fatter. So kind of take a look at my pen up here, if you would. Normally, since you've all done assignment 28, I know you have. Normally, when we go, say, to the right one, how far up would we go? I'm not going to go up 1. I'm going to go up 2. Now, the reason I did that is because the 2 that's in front of the x squared, let me underline him up here. He says, hey, I'm going to take all of your 1, 4, 9, those cute little things you figured out. I'm going to take them all and times 2 them. I'm going to double them. That's where the physical change comes from in the parabola. We call this a vertical stretch. You don't need to know that, but when you see the graph, you'll realize, oh, that kind of makes sense why we call it that. It feels like you're actually grabbing the parabola by its top and bottom and stretching it, which causes it to look like it gets skinnier. So when I go out 2, how far up would I normally go? How far up am I going to go? Good for you guys, 8. I would go up double times 2 what I normally would. So I'm going to go out 2 and then up 1, 2, 3, 4. And again, 1, 2, 3, 4, causing it to stretch. And as you can obviously see, there's not enough room to go again, because if I went out 3, how far up would I have to go? 18, right? I thought I maybe heard it. I wasn't sure. 18, good. And clearly we don't have enough room for that. So this graph has undergone, again, what we call a vertical stretch. And you get to graph it. I mean, it's not easy. As I said, I think on the first day, you come to a point where if you're good at math, without a doubt, the hardest part is making the graphs not look like complete and utter garbage. So you might find yourself spending a lot of time just sketching, and it's worth the time because I'm going to make fun of you if your graphs look really, really bad. They don't have to be perfect, but they should have curvature to them. So yes, Gavin, they should look curvy. And again, it ain't easy, especially on stretchies. You'll find the fatties, and we're going to get to a fatty here in a little bit. Fatty graphs are easier because they flow more smoothly outwards. But skinny guys, yeah, trying to not make them look like straight lines kind of sucks. Yeah. Mhm. By the whole thing, do you mean like our vertical jumps are 149s? Yeah, I'm going to get rid of this now, and we'll go find a problem to address what Alyssa's talking about. Something like this? Yeah. No, because then it won't be y equals anymore. I wish we could go fraction killing, but this only, when you graph a function like this, it has to say y equals. As soon as you multiply the whole equation by 3, then this one would say like 3y equals, and no longer is it a graphable function. Does that make sense? I wish we could, believe me, especially when you see what we're about to go through in problem 3, you'll really wish we could. So I apologize in advance for what we have to do. I think we should try problem 3. Problem 3 is a beast, and you're not going to like it. So let's try. I'm skipping 2 for now. Just wanted to take a look at 3 so you can see how utterly uncomfortable this process can be. So what is A in problem 3? A is 1/3. So I'm going to use this as my workspace up here. And what is B? Good. And feel free to use a calculator for this process. Some of you won't want to, some of you will, because it gets pretty ugly. The formula doesn't change though. That's the good news, is we're still going to rock the negative b over 2a. And so we're going to do the opposite of b, divide that by double a. And here we go. So what is the opposite of b? So I'm going to put positive 8/3, and then I'm going to divide it by, I'm going to make a bigger division sign. So the little fraction that I put up there for opposite of b, I want it to be dwarfed by the like granddaddy, big papa division of the problem itself. And then on the bottom, I'm going to do double A. What's 2 times 1/3? 2/3. And this is always where, as a math teacher, the room is split. It's usually right in half. There are some of you that look right at this and know that the answer is 4. There are some of you that are not comfortable with that, and you might be inclined to type into your calculator, like you could type this in. You could type in 8, so make sure you do parentheses, 8 divided by 3, close parentheses, and then hit divided by parentheses 2 divided by 3. And through complete and utter black magic witchcraft, your calculator, when you hit enter, will say 4. Did it work? Good. Now, a little bit behind the scenes, if you're someone who doesn't really engage in that calculator tomfoolery, just bear in mind the old copy dot flop. So what 8/3 divided by 2/3 really is 8/3 times 3/2. Good for you. So this is actually 8/3 times 3/2. Remember that we flip the second fraction when we divide, and then you can see the threes cancel, and you're like, oh, hot dog, 8 divided by 2 is 4. So at this point, we can now say that the vertex is at the following point, 4, comma, who the heck knows? With the green light to use calculators, you may not feel the burn. That might feel like an okay process for you. But it doesn't get any better. I mean, we keep going now. And the trouble is, where there were fractions, there will be fractions. And going back to what Alyssa asked, gosh, do I wish I could get rid of the fractions, but I can't. You're not allowed to kill fractions in an equation that's not really negotiable like this. So now we have to take our 4 and we have to plug it back into the problem. So it's going to say, and I'm going to show some work here. It's going to say 1/3 of x squared. What's 4 squared? So I'm going to put 1/3 times 16 minus 8/3 times x. And in place of x, I'm just going to put 4. And then I'm going to put plus 4/3. Anyone panicking yet? You okay? Calculator, would be more work than it's worth at this point in the process. What I am going to do is I'm going to melt these all together. I'm going to melt them into just like one fraction each. And so the first one is 16/3. What's the second one as a fraction? This one. You don't actually have to. If you just do 8 times 4, what do you get? So this would just be 32/3, because the 4 is like a 4/1, right? And then you don't have to modify the 4/3. Like there's no modify, like you don't have to multiply or anything like that. So now how convenient, how nice that the bottoms are all the same. That means I can just add all the tops together. So I'm going to draw a little blue shape around all the numerators just to draw your attention to what we actually have to do. What is 16 minus 32? What is negative 16 plus 4? So my answer is negative 12, but it's over 3. And what is negative 12/3? That's a lot, guys. And for a lot of you, that's just straight misery. But I can't really do more for you than that. I mean, again, you could type a lot of stuff into a calculator. And if you're really good with a calculator and you know like when to use parentheses and all that stuff, it'll still give you the same answers. But having said all of that, like, whew, wipe sweat from brow, we have now found the vertex, and it's time to proceed. So the vertex of my graph is going to be at the point 4, -4. Got that? So I'm going to head down to the graph now. And again, the vertex is at 4, -4, and I'm going to put a dot there. That's a lot of work just to figure out the stupid vertex. Now, there's a number in front of x squared, and I scrolled too far. What was in front of the x squared? Negative. Just 1/3? Okay, so 1/3 is going to be a very powerful number for us here. The fact that it says 1/3 means that we're going to take all of our vertical normal jumps, and I need you to get this stuck in your head. It already is, but I need it to get super stuck. Remember, our normal ups are 1, 4, 9, 16, 25, so on and so forth, right? I'm going to take all of those and calculate 1/3 of them. So, for example, if you were to go out 1, you would normally just happily go up 1. What's 1/3 of 1? It's 1/3. Good. And so I'm going to go out 1, and I'm going to go up roughly 1/3 of the way to 1. I'm taking all of my would-be normal verticals and essentially dividing them by 3. That's what it means to take 1/3 of something. When we go out 2, we would normally go up 4. What's 1/3 of 4? 1. 1 and 1/3. Your calculator will do it for you. If you just type in to do 1/3 of 4, you literally just type in 4 divided by 3, and it will say 1 point boatload of 3s. So you interpret that as, oh, so when I go out 2, I go up 1 and 1/3, which looks about like that. You can see here we've got an instance of a fatty graph. These should be easier for us to sketch. But the bad news with fatty graphs is you can always graph more points, and your cranky old teacher wants you to graph always as many as can be fit in the grid provided. Let's keep going. You will have graphs where I remember in the past I've had graphs with like 13 graphable points. It can happen. So not in this case. If we go out 3, how far up normally would we go? 9. What's a third, though, of 9? So we will go up exactly 3. You see that we're basically doing what we've done before, but the number in front of x squared is our vertical modifier. He either stretches them to be more extremely quick growing, or he like squashes them down and makes the graph like essentially flatten like a pancake. If we were to go out 4, how far up would we normally go? 16. What's a third of 16? Or 5.3. Good for you. We're just dividing by 3. This will be it, because we're actually, we can be done after this, because we could keep going to the left, but generally if one side runs out, I'm okay if you just bail. So again, if we went to the right 4, we would go up 16. 16 divided by 3 is 5 1/3. So I'm going to go up 1, 2, 3, 4, 5 1/3. And I would be happy if you got that many points. Again, could you keep going left if you wanted to? Sure. If I went left 5, how far up ought I go? 25. But what's 25 divided by 3? 8 1/3. So I could go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8 1/3. If you just wanted, sometimes it's nice to have more points. It gives your sketch more points to anchor onto. You certainly don't want to try to do any more on the right because you're out of grid space. What do you think of that? Is it okay? Yeah. All right. Let's try another one. So I'm going to erase this now, okay? All my points are going bye-bye. Hustle up. It is, isn't it? There's something about it when it's got the smoother, less angled curve. It's just easier on the pencil. Good point. Yeah. So let's go hunting for something else that's interesting. How about, does 6 look bad? I wanted to do something like number 7 just because it opens downwards. So let's talk about number. So I'd let you choose between 4 and 7. You guys pick. 7's fine with me. So, right. So really the process isn't all that different. I just have to be cognizant of the fact that there's a negative, and I don't want to, blow it at the end. I've done all this hard work to find the vertex. I'm there. I understand the whole power of the 1/2. Just got to make sure you graph it the right way. So what's A? Negative 1/2. So A is negative 1/2. And B is negative 2. And so I'm still going to glue myself to the negative B over 2A formula. What's the opposite of B? 2. And I answer a lot of questions in high school math classes about what's about to happen. What is 2 times A? It's negative 1. And there's a 99.996% chance that at least 3 of you want to know how we got that. So you just don't like to ask. So I'm going to show you that what just happened on the bottom was we did 2 times A. And what that looks like is 2 times that. And the rule with multiplying is that both of the things have to be fractions. And so behind the scenes, those of us that knew what we were doing, we took 2 and wrote it as 2 over 1. And then you can either cancel the 2's or not, but you wind up with like either 2 over negative 2 or negative 2 over 2, however you want to say that. Is everybody okay with the fact that we said negative 1? Nice. So what overall then is the final simplified value of negative B over 2A? It is negative 2. So we can now say the vertex is at negative 2 something. Something is a mystery. So to calculate the something, my job is now to take my hard-earned X value that I found and plug it back into the formula, not the formula, but the equation. And that means you put it there and there, right where those little red arrows are. So in the first one, what is negative 2 squared? 4. And what is negative 1/2 times 4? It is negative 2. Now, in the second part of the function, the equation, it says minus 2 times x. Think of that as negative 2 times x. And what's negative 2 times another negative 2? That's a positive 4, a plus 4. And what is negative 2 plus 4 plus 4? Is positive 6 for sure. So our vertex finally, oof, we made it, is at the point left 2 up 6. From this point, I don't need to show any more work. That's everything. That's, to me, that's all the heavy lifting has been done. If you understand the 1, 4, 9, 16, 25 and how to modify it, the rest is easy. So I'm going to erase a bunch of stuff on my board here, and I'm going to switch to a fatter pen, and we're going to plot some points. So let's begin by going to the vertex. The home base is at left 2 up 6. So we go there and dot that. Right, so we're going to take all of our vertical jumps. We're going to divide them by 2 because that's what it means to take a half of something. And we're also going to go down. So when I go out 1, where will I go? You always still go out 1. You always go out 2. You always go out. Never change your outs. So when I go out 1, where do I go? I go down 1/2 because that's half of 1. When I go out 2, it's always important to ask yourself the question, what would I normally do? If I went out 2, I would normally go a jump of 4. But half of 4 is 2, right? So I go out 2, down 2. It's all about the number in front of x squared now. When I go out 3, I would normally go down 9. What's half of 9? 4.5. So I'm going to go out 1, 2, 3, down 1, 2, 3, 4.5. All these points are tweeners. They're between lattice grid lines, and that's okay. Get used to that. When I go out 4, I would normally go down 4 squared, 16. What's half of 16? So I'm going to go out 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6, 7, 8. And I bet we have maybe room for one more. Let's press our luck. If we were to go out 5, we would go down 25. What's half of 25? 12.5. So let's see if we have room to go down 12.5. Do you? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.5. And that officially would be us maxed out. So that one has 11 graphable points. It'll always be usually be an odd, your vertex, and then 2 on each side. So scale of 1 to 10. 1 is no clue. 10 is, this is the easiest thing I've ever done. Where are we at? 9, 7, 6. Not bad. Yeah, I'm with you. Like Gavin said, sketching the stupid things, I said it before, it will wind up being the part that you spend a lot of time on. So I'm going to cut the recording here and let you guys know, unless there's anything else on the worksheet that catches your eye before I cease the recording. Is there anything else that you'd like to go over? I'm all yours if you want. All right, you got this. I'm going to cut this off. The remainder of the time is yours. Just crank away. Do them in whatever order you want. If you find a vertex and it doesn't fit on the graph, the computer makes these, okay? It's never going to place a vertex outside the graph. So if your vertex doesn't fit, you did something wrong. All right, cool.